Hello everyone. Today I will be presenting a project concerning time series classification. The dataset that is used in this project contains 87 samples of sequences with 512 steps each. These sequences are RI intervals extracted from ECG data recorded for each patient. The samples are divided into two groups, namely a group of healthy individuals and a group of stroke patients. The main objective is to identify stroke patients from ECG data. The modeling of the data can be broken down into four parts. The first step is to embed a time series into an Euclidean space as a point cloud so that a topological space can be constructed, which serves as a foundation for any further analysis of the time series. Next, with a topological space constructed, persistent homology can be applied to it, which is a tool that tracks the evolution of high-dimensional wholes. The result produced by the persistent homology will be recorded through a vectorizable representation, which allows the use of machine learning algorithms to do the classification. Next, I'll be talking about how the embedding works. For any time series, the embedding theorem requires two parameters, which are the time delay and the embedding dimension. With those two parameters specified, the time series can be converted into vectors of the following form. There is no universal method for choosing the right embedding parameters. In this project, I choose my time delay to be the number that maximizes the average persistence entropy over all samples, and the dimension is chosen to be 3, mainly for the computational consideration and to avoid any redundancy caused by the noise. After the embedding, topological spaces can be easily constructed using the Rips complex, which forms simplices based on the pairwise distance between points, and it uses points in the point cloud as vertices for those simplices. With the topological space defined, the next thing is to define the persistent homology. The first part of it is the homology group. Loosely speaking, homology groups count holes in various dimensions of a given topological space. Consider all the chain groups on the topological space, which are just collections of simplices of the same dimension. Define the boundary maps between chain groups. The homology group is defined as the quotient. The second ingredient is a filtration. In this case, the topological space or the Rips complex has a natural filtration induced by the distance parameter. So tracking the changes in the homology groups with respect to the filtration gives the persistent homology. The information captured by the persistent homology is stored in a persistent diagram. Basically speaking, the diagram records the time when a new topological feature appears and the time when it disappears. However, due to a lack of Euclidean structure, the space of persistent diagram is not suitable for any statistical models that uses a simple inner product. Hence, it is necessary to consider other alternatives. For example, the persistence image, which is a stable representation of a diagram and it is vectorizable, which means that it can be converted into vectors for machine learning purposes. Consider all coordinates on a persistent diagram. Rotate the diagram so that the points are not concentrated in the upper triangular area. Define a Gaussian function and a weight function. The persistence surface is just the weighted sum over the domain. Since the diagram is clearly a square, the persistence surface can be discretized by smaller boxes, or pixels, integrating over the discretized domain to obtain the persistence image. By construction, a persistence image requires three parameters, which are the variance for the Gaussian, resolution for the output, and the wave function. Results from simulation indicates that the persistence image is insensitive to the variance and the resolution. However, the choice of the weight function depends on the situation. In some cases, points with low persistence may be more important than the others. Here are some examples of persistence image. The top row contains images for stroke patients, and the bottom row is for healthy individuals. By simply looking at the plots, it is clear that there is an observable difference between two groups. Lastly, flatten all the images into vectors and stack them together to create a matrix so that machine learning algorithms can be applied to. Here I used 4 different algorithms to do the classification. As a comparison, the same algorithms are applied to the conventional predictors as well. Judging from the accuracy, the topological predictors indeed outperforms the conventional predictors.